So here are the eBooster bypass valve options. This guy is what I was originally going to go with. It's just a passive spring-loaded bypass valve, and it would sit in a housing like this, a two-piece housing that comes together with some sort of a V-band or something, and the charge air from the turbo would go through the valve in this direction to bypass going through the eBoosters. And so this passive spring-loaded valve would sit inside the housing. This particular valve is actually a bit small, and this housing is designed for a larger version of this. But this O-ring seal would seal against the inside of this housing. And when the valve is inserted, mounted, that valve is just slightly compressed. So it's always, passively maintaining a active seal against the housing with this O-ring. So then this other half would come and kind of sandwich the two. And what happens, the way this works, is that it just operates on a pressure differential. So the valve is always closed unless the pressure on the back side of the valve is lower than the pressure on the front side of the valve, at which point when the pressure past the valve is lower, it essentially sucks, or the pressure on the high side pushes this valve open to allow the air to flow axially through the valve. And that scenario occurs when the turbocharger is feeding this valve and feeding the eBoosters, and when the turbocharger is generating more boost pressure than the eBoosters are providing, which this side would see any of the boosted air from the eBoosters, and this side would always see any of the air coming just from the turbocharger compressor outlet. So once eBoosters are kind of out of the steam, up towards the higher RPM range, the turbocharger's out boosting the eBoosters, and this valve pushes open and allows the air to go through the compressor stage of the turbo, be pressurized, and then completely bypass the route through the eBoosters. And this setup is really great. It's a very simple valve, very reliable. The only challenge is that right now I can source valves that are built for very small engines, which is typically where these types of setups are used. And I need a much larger valve to support the airflow to my setup. Plus, my setup's at the very back of the car, and so again, any pressure drop or pressure loss that I can avoid would be great. So, the alternative that I'm going to attempt is to use an electronic throttle body. So I've already modified this one, and there's one definite benefit to using something electronic, is that because this valve stays naturally closed, it forces all of the air during idle and low load conditions to go both through the turbocharger compressor and through the eBoosters. And so both of those things sitting at the back of the car, there's a long charge or intake route, plus the turbo compressor and the eBooster compressors all provide some degree of restriction that isn't optimal for light load when those guys aren't working hard. So what an electric valve allows me to do is it allows me to have a default position, which is, I've changed the springs in here to do this. So the throttle body or valve defaults to an open position, which is both nice because at idle and low load, the air doesn't have to go through the eBoosters, and it can travel just through this large throttle body and make its way with very little restriction up to the front of the car. But also, this valve, in defaulting to open, if the motor fails, or if the valve electronically fails, then when this valve defaults to open, that means that the eBoosters aren't going to see a lot of boost pressure really ever. So this is kind of a nice little safety feature to have. The only challenge is that it's additional complexity. So I took out the springs that came with the throttle body, and I essentially just wound from some spring steel that I bought, or stainless steel that I bought, that was the same diameter. I rewound these two springs in the opposite direction, and I considered the preload that these springs are designed for. And so with them installed in the body, it now defaults to somewhat almost fully open, and I got to work against the spring just a little bit to go to a fully open position. And then, of course, you're working against the spring to go to a fully closed position. So here there's a little set screw I can set as the throttle stop, and that'll allow me to ensure that the throttle blade is closing as much as possible while not sticking, because that's one of the challenges with throttle bodies is as these butterflies come to a full stop and actually mechanically rub against the housing ID, that throttle plate can actually stick and bind on the housing. Plus it's a wear issue. So that throttle stop will allow prevent that from occurring. And then I will just need to control this guy with my Arduino. So I need to figure out how to send it the right messages. And essentially the Arduino will be looking at the pressure differential, just like this valve would be seeing, except the Arduino will be looking at a pressure differential sensor, essentially two map sensors on either side of the body. And when it sees that the pressure on the outlet side of the valve is lower, significantly lower than the pressure on the inlet side of the valve, plus it'll rely on knowing when the eBoosters are actually being commanded to boost. So those two conditions will drive this valve to close. So the valve will only close in this setup when the eBoosters come on. And any other time when the eBoosters are out of steam or when they're not operational, the valve will default to open, and whether it's the natural resting position or move this blade to go fully open, I'm not sure it'll make much of a difference. This is a 102 millimeter throttle body. My charge plumbing is 3.5 inch, so this is about a 4-inch valve. So the valve will definitely not be the limiting factor or a big restriction really at all in the system. So we'll see. As far as sealing, this valve is not perfect. So if you put it up to the light, you can see a little bit of light around the valve. And I've messed with the butterfly position to try to improve that. But what I have found is that there is an epoxy-based compound used on some early GM carburetors for their secondary valves that is applied to the inside diameter of those bores, and it's graphite impregnated, and it's actually designed to improve the seal around the butterfly itself. So I may ultimately end up trying to source some of that and applying that to this housing just to further seal up this butterfly blade against the ID of the housing. But any leakage that this valve has when it's fully closed will just reduce the efficiency of the eBoosters because their energy will be going into pushing air up to the engine, and some of it will be leaking past this valve to kind of recirculate, but very, very little bit. I mean, the light that you can see through this valve is hardly anything. So we'll see. I may not even need to go down that route, but if it does present a challenge, then I think I have a solution to create a little better of a seal around this this interface. So time to reassemble the throttle body, make sure that I've got everything set up right, and then start to figure out how to get this guy working with the Arduino. And if this thing doesn't work out at the end of the day, I can always resort back to designing just a larger version of this, where it's a very light spring, a large valve face. I probably would end up with about a 3.5 inch diameter valve face and a 5 inch diameter body. That would allow this area here to provide minimal restriction once the valve pushes open. But this is all part of the experimenting to make this system work nice and smoothly on a car that never had it. So, hope that was helpful.